Bonjour. Great. Yeah, it's 10:20. So there's nothing more to announce except for the point number 3 and 4 yesterday. So we'll go ahead and start lecturing. So morning, Vincent. I believe that's your name in English. Hongru and Leo. Okay. Now, first topic. Let's try to wrap up RDT 2.2. All right. So if you recall yesterday, RDT 2.2 is essentially RDT 2.1, but that's not use two packet formats, ACK versus NAC. That's just use one packet format, ACK, but carrying a sequence number. And that sequence number should indicate always, let me quote, the last packet received OK. All right? And today we're going to try something a little bit different. So previously 2.0, 2.1, what Polly did is just, introduce the finite state machine of these RDTs to you. Today, let's try. If we could gradually develop RDT 2.2 from RDT 2.1. So that way you see, as a network engineer, you might be able to, based on what you learn here in the class, these finite state machines, and develop your own RDT 2.3, 2.4, or RDT 3.0, 4.0. Good. So let's start today from developing the receiver side of RDT 2.2. Yeah, and morning to Xuan, Blaine, and Wei Shan. Now, receiver of RDT 2.2. Now let's try to develop RDT 2.2's finite state machines. So here what we will do is to borrow from 2.1 and start from the receiver side of the finite state machine. All right, so yeah, initial state is wave 40 from below. So we're expecting data 0, and we get 1 if it's not corrupted and indeed carrying sequence number 0. Then we extract data, pass it up to the application layer, generate an ACK packet with the checksum, and then send it out. Now, if it's 2.2, we'll be generating an ACK packet, all right, but this ACK packet should be carrying a sequence number, isn't it? And according to 2.2, the sequence number should be the last data packet received OK. And what is the sequence number of the data packet received OK? Well, we just actually received 0. So, yep, you're correct. The ACK packet we're generating here for RDT 2.2 should carry sequence number 0. And so once we finish all the actions, we'll be finishing the transition and move to the next state, wait for 1 from below. And if we get packet 1 coming in, passing these conditions, so indeed carrying sequence number 1 in this data packet, then similarly, we take the data out, generate ACK, and send it out. And here, the ACK sequence number will be what? Data 1, the sequence number that we just received. So as a result, we could actually conclude the receiver side of RDT 2.2 should look more like this. And I'm ignoring the upper right part of the receiver's finite machine. So receiving a packet, not corrupted, carrying sequence number 1. The ACK packet will be generating, of course, it needs to be an ACK packet format carrying checksum. It also carries what? The sequence number of the data we just received, OK, and which is 1 here. So for this other transition at the top, then it will be make packet 0 ACK checksum. Now, hey, the receiver side of RDT 2.1 actually have all these other transitions, right? So we only handle this part and extend it to 2.2. We will still have to extend these transitions so that it will work for 2.2. Now, these are actually exact mirror of each other, so let's just focus on one side. Okay. Now, let's pick this transition first and see if we could evolve it as well into 2.2. So this is receiving a data packet, but it's corrupted. So in 2.1, we send a negative acknowledgement. But for 2.2, we don't send negative acknowledgement packets anymore because we don't have that format. Instead, we send ACK. But we have to carry a specific sequence number to indicate whether this is really a positive acknowledgement or a negative acknowledgement. So, the rule of thumb generating the sequence number there is what? Who is the last data packet received OK? Now, Receiver is currently waiting for data 0 coming from below. So what that means is that the last packet received OK should be carrying sequence number 1. So ACK here should give the sequence number of the data packet last received OK. So yep, it should be ACK1 here that we're sending back to the data center. Now, what about this other transition? Receiving a packet, not corrupted, but carrying sequence number 1. This is not the data 0 we're expecting. All right. How can this be happening? Yeah, so this is the very odd situation where the previous data, ACK, being sent back to the sender gets corrupted, if you recall. Yeah, ACK packet or negative acknowledgements can be corrupted now, right, in version 2. Now, if negative acknowledgement is corrupted, sender simply retransmit, no problem. But if positive acknowledgement gets corrupted, sender also retransmit. And that is this odd situation here. You already sent back an acknowledgement for data 1, and yet it's receiving data 1 again. Yep. So this is the situation. ACK packet gets corrupted, and so you're receiving a duplicate of data 1. So we do not extract data and pass it up to the application because that's going to repeat words, repeat letters, repeat sentences. Okay. So we only send back ACK. And this ACK should be what? Acting the last packet received OK, therefore also carrying sequence number 1. Okay. Now, if you look at this guy and this guy, both transitions, the actions they'll be taking will be identical now, right? Both sending acknowledgement packets carrying sequence number 1. So then perhaps we could just combine the two transitions. Receive a packet from below, checking if it's corrupted, or carrying sequence number 1, send ACK packet 1. Right? And you know what? ACK packet sequence number 1 is already being generated here. Send PKT, if you do not replace this variable's value, it will remain the same. And so if we just simply call this, then yeah, we just combine the two transitions and make it very brief, like this. RDT, either corrupt or carrying sequence number 1, simply send back the send packet that has been generated here, which is an ACK with sequence number 1. Voila, so that was the receiver. And we managed to develop from 2.1's receiver to 2.2's receiver. Now let's try to do the same for the sender side. Now let's try to develop the sender's finite state machine. Again, let's borrow 2.1's sender finite state machine and start from there. This is the initial state. We wait for call from above. And if there is 1, then we generate starting from packet 0. And then we enter that wait for ACK state. Now in case a NAC is in, we do have this is NAC check, isn't it? Okay. So if that is the case, we retransmit the data. Otherwise, everything is fine, and this is a positive ACK, so we do nothing and move to the next state and gets a call again from above. But the thing in 2.2 is this. Well, there's no such thing as negative acknowledgement packet. In fact, both positive, both negative acknowledgements are just ACK and carrying different sequence numbers. So this will also be a is ACK check, okay? But the difference is going to be the sequence number they are expecting being different. So what should be the sequence number we expect here to pass so that we move on to the next state? We are expecting 0, right? So the sequence number here should be carrying 0. So we should be checking is ACK and particularly sequence number being 0. Therefore, we can move on. Send the next packet. If everything goes well, we should be getting another ACK packet, then carrying sequence number what? 1, because we just sent out packet 1. The NAC here, check can no longer be valid and will be also doing the is ACK check. But what should be the matching sequence number here to trigger this action? Well, we just send packet 0. If packet 0 was corrupted, the receiver would be what? Sending the last data packet received OK. So that should be what? Sequence number 1. Similarly, for the check here, it should also be is ACK, but sequence number what? 0. And that takes us to the sender side of the finite state machine. So we change this line as well as this line. So this line is what? Expecting 0, so check whether the sequence number equals 0. This is also now is ACK, and this should be carrying sequence number 1. So you see, in RDT 2.2, the sender side just do is ACK check with the sequence number. Similarly, at the receiver end, the receiver generates only ACK packets, but with the sequence number that's always indicating the last packet received OK. Good, so we're done with version 2, and let's move on to version 3. This is the case that some of you guys have pointed out, that underlying channel that we are trying to address with the RDT could have bit errors, but it could also have this thing, packet drop. And that's even worse case, because when there is a packet drop, receiver won't be able to receive a packet for checksum at all. There's not going to be any feedback back to the sender. So how are we going to deal with this? RDT 3.0 is there to help. No, Tanya, I'm just going to talk about it. And this time, we're going to, try something else as a change as well. Instead of telling you what the idea of RDT 3.0, how we address packet loss, let's try exercising our brain, solving quiz 19. So it's open-end, but it's a problem very similar to this. Having an underlying channel that's not reliable, but how do we make sure that the message gets through, okay, instead of being dropped? And that's quiz 19. All right. Tanya, now more comfortable? All right. So this is quiz 19. Polly likes to read all kinds of books, including fantasy novel. Okay, so this is what Polly borrowed from the series called The Lord of the Rings. Okay. So I think in one of the volumes, there's this thing called the Battle of the Helm's Deep. Where is Helm's Deep? It's here, in the middle of the map here on the right. Okay, so people living there are called the Horsemen people, and the tribe is called the Rohan. Okay, now Saruman, the evil wizard, okay, and his troop is pushing in and try to conquer Rohan. Okay, so the king of Rohan here, okay, under trouble, has no choice but to call for help. Okay. Luckily, there are these other people living in Gondor, down here in the map. Okay, so these are also human, but unlike the horseman people, Rohan, horseman people are taller and riding horses and things like that. Gondor, they are just normal human beings like us. All right. So, King of Rohan calling help from Gondor. So the way they do it is to send messenger. Okay, from Helm's Deep to Gondor. But you see, in the middle, they also have a unreliable underlying channel called the White Mountain. And this place, White Mountain, is full of these creatures. Okay. People eating orcs. Okay, so the messengers can easily be, well, dropped or eaten. Okay, now you pretend to be the Gandalf the Wise, Gandalf the White. How can you make sure Gondor gets the message, gets the call for help? All right. Now go to the Slack space, find the W8 Quiz 19 channel, grab Gandalf the White. Gandalf the White. Yeah, I think Gandalf is both white and wise. Okay, so the best kind of creatures are both smart and kind. Otherwise, hey, one could turn out to be Saruman, the evil wizard, very capable but doing bad things. Not good. All right, so grab your teammates. You have 5 minutes. Okay, feel free to be creative here. Okay, this is also extra point opportunity for the quiz part. Those that are very creative earn extra points. And let's go ahead and start.
All right. Okay, so this is actually one of my favorite quizzes in the whole semester because I get to see all sorts of interesting ideas coming from you guys. I see that some of you go with the fantasy solutions, but some of you also go with the practical solutions. What if you don't have that much magic? You see that magic power, you don't want to abuse it. All right. Hey, when people see you using magic, they would try to target you and somehow, okay, get you to help them doing things. All right. So let's see. Team 14. Okay. Jade is speaking on behalf. Shoot some signal to the sky. I think this is what the Rohan people did, right, in the novel. They have these fire stations and they lit up the fire, creates smokes up on the sky, and there are like the multiple stations relaying each other, and eventually the signal reaches Gondor. Yeah. So hey, orcs don't eat smoke, so that works. Okay. But orcs may eat people guarding the fire stations. See, build a road bypass the mountain. Sure. Well, that is a little bit challenging. Yeah. Maybe going around instead of have the messengers running through the mountains. Maybe run across or around the mountain. Right. Detour. Cool idea. And Agent Zijun was saying, using my magic power. Of course. Yeah. You are Gandalf the Powerful as well, of course. Let's see. The other overland might be a good choice, or applying an ACNAC system. Other transmission. So maybe instead of going on the land, going over in the air. Niming here is flying creatures are more likely to survive. Yeah, seems so. So you can probably send a pigeon or eagle, yeah, over in the air. Or send more than one messengers. Okay, sure, and yeah, redundancy. That's a technique that's commonly used. Okay, in case you see that there might be losses ahead. Okay, and you hope at least one of the messages survive. Kain here, Kain. So I hope that I pronounced the name right. Some flying creatures. Wait a reasonable time, and if there's no response, so you ask Gondor to respond, right? Very good. And the response can be a firework, or some messenger coming backwards, I guess. Just take it as a loss. If after some time no response, then take it as a loss and retransmit. Remember in 2.1, if the ACAC is corrupted, just retransmit. With the sequence number, the receiver will be able to deal with potential duplicates. Okay. Very good. So Polly was saying that, yeah, Cayenne here is RDT 3.0, guys. So what Kayan was saying there, the solution, waiting for some time and try to send another messenger again. Okay, let's see. Team 15 solution according to Wikipedia. All right. So Gandalf is able to skillfully use all kinds of magic, fireworks. Okay, convincing hobbits to transmit the message somehow. And with the rings, they can go invisible, isn't it? Okay. She continues to send messages for help until receiving an egg from Gondor. Okay. And there are two kinds of methods to send messages. Direct message by animals. Subspecies. So they look less suspicious to the orcs, or orcs probably prefer eating people instead of other animals. I see. Indirect message. Such as fireworks, sky lanterns. Very interesting. That's in fact quite Taiwanese. Okay, team 4. Estimate the time it takes. Estimate the time it takes to send a messenger to Gondor, and for Gondor to send the messenger back, or the messenger runs back to Helm's Deep to notify the king that Gondor has received the message. Now, if the messenger does not come back in the estimated time, then send another messenger. Ouch. Or send the same messenger, since that he get it through the first time, right? He probably knew some tricks to get around orcs. Ask someone. Ask someone who can run a long distance, a marathon, to send a message. So this guy then can maybe run around the White Mountains to avoid the orcs. Send Gandalf's ego. All right, Victor. Send a soldier. A soldier can shoot a firewalk. I see. Okay. So the way back is a little bit magical. Sure. So it's the other way around. Gondor sends an eagle or do some magic. Okay, visual solution. Great. Love it. Yeah, so it's very clear, right? Just fly through the air. Okay. Yeah, Gondor's trusted eagles. Yeah. Okay, you guys like the eagle solution. Direct human messenger. Morse code. Okay, cool. Okay. But Morse code is very 20th century, okay? Since several, or is it 19th century? Okay, somebody look it up for me. I think it's 20th century. Send several messages, half of them will be killed. Oh, okay, that's quite a casualty. Yeah, the more people, the better. Okay, good. So great. So I think that you guys get it. I mean, in the novel, of course, you can use fancy magical solutions. But in the real world, you could do what? Offline communication. What was it? Out of band communication, right? So you send messenger, you send also ego at the same time, or messenger. In the meantime, you do the fireworks. Okay. One also say that send more messengers. Okay. But eventually, in order to get acknowledgement, you want the Gondor to send something back. If that message coming back is received, then it's okay, good. I don't need to send repeatedly. Otherwise, you retransmit. So, guys. I see Belen saying something. First long distance message in dot dash It's called Travel from Washington. Ah, okay. Oh, right. It's 19th century. But very close to the 20th century. Okay. Thank you, Belen. Good that you look it up. Okay. But guys, you see that you can come up with the solution yourself. So the idea of 3.0, you see, it's no longer fancy. And a lot of times, so the challenging problem you see ahead, try to abstract that problem you're running into and see if you run into the problem before, okay, in other domain. And you can see also historically how people solve that problem, and you borrow that solution to this seemingly very challenging problem you're solving. That's always the way you get the idea first. Okay, and maybe you will evolve the idea and adapt the idea to the environment that you need to implement the idea. Okay, so generally how you solve any challenging problem. Okay, try to associate from the problem here that you're facing to maybe other problems that are very similar but solving out the domain, and you borrow solutions there for the problem here. Okay, good. So RDT 3.0, then the idea is very simple. Okay, this is coming the next video.
Now, the last version of RDT, the RDT 3.0. In version 3, we're going to make it very general. So there could be bit errors in the data packet, in the acknowledgement packets, but there could also be losses of the data packets or the acknowledgement packets. So the new assumption here is very general. The underlying channel might have bit errors, but it might also have packet losses, both at the data side as well as the ACK side. Now, all these mechanisms we have in version 2, checksum, X, retransmission, and the sequence numbers to avoid duplicates will help, but only help for, bit errors. So, in case of packet losses, not enough. So we need to add extra mechanisms. And the extra mechanism is this. The sender waits for some amount of time for the ACK to come back. If the ACK does not come back within the time window, then retransmit the packet. Okay, so retransmit the data packet if no ACK comes back within that timeout interval. All right, so what we're doing here is to require setting of a countdown timer per data packet being sent. Okay, so when the data being sent, timer gets started. That timer is going to tick. If ACK comes in before the timer expires, cancel the timer. If there's no ACK coming in and the timer expires, retransmit the data packet. Right? So that's pretty much all to address the packet loss issue. Now, hey, some of you might be wondering, what should be the timeout interval there, right? Hey, internet delay could be changing quite a lot over time. So these data packets can be just delayed, or the ACK packets coming back can just be delayed. So in case they are slightly longer than the timer that we have set up, then we will be retransmitting data unnecessarily. Yes, okay. Some of the retransmissions might be unnecessarily a duplicate. Just like when ACK is corrupted, the retransmission from the data sender in 2.1 is also unnecessary. But it's okay. We already have the mechanism right there, which is the sequence number. That's going to address the duplicate issue. So no worry, even though if we didn't set the timer quite right. It's just that there'll be a lot more unnecessary retransmission if the countdown timer is too short. All right, so hey, determining what is the duration for the countdown timer, that is also an art. We'll also see later in TCP how that is calculated, how that is estimated. All right, so sequence number is necessary again in RDT 3.0. The receiver needs to specify the sequence numbers for the ACKs, just like the data side needs to specify the sequence numbers for the data packets. And this is RDT 3.0 sender. Well, the usual technique, let me draw a line. So we just focus on one side of it, you'll see that the other side is similar. So what do we have here? Starting from the initial state, get a call from above, generate the packet, starting from sequence number 0, and what? Wow, we have these timer stuff, right? starting a timer. And this is the transition next. If everything is going smoothly, receiving an ACK, it's not corrupted, and it's indeed ACK for 0. Then what? Stop timer. Now, if things don't go all that well and the timer expires, then retransmit the packet and start the timer again because, hey, we just sent the data again, then the timer needs to be refreshed. Yeah. Now, what is a bit unusual is in this transition. So what is this transition in 2.2? Well, yeah, the packet coming back from the receiver, if it's corrupted, or if it's clear that it's a negative acknowledgement, previously what did we do? We retransmit packet, right? Like calling UDT send packet here. But we actually do what? Nothing this time. Would that work? If it's, yeah, corrupted ACK or a negative acknowledgement, and we do nothing, would that work? You know what? Hey, there's this transition, right? Yeah, so sender here would just not work in case we get this explicit, okay, signals from the receiver, something is wrong. But eventually the timer is gonna fire as well. So that packet is gonna be retransmitted. It's just that, hey, with these situations, we're just, gonna wait. So we'll just always wait until timeout. How do you like that?
How do you like that? And some of you might be wondering, hey, is the next video the receiver side of RDT 3.0? You know what? There's no change in the receiver end. Right? Receiver simply gets a message, do the checksum, sends ACK with the proper sequence number. If a packet is lost, receiver won't know anyway. So there's nothing else receiver can do. So in RDT 3.0, the receiver is the same as RDT 2.2's receiver. The only change is on the sender side, and the changes are all about the timers. Now, some of you might be going, yeah, just send again, and only the sender can detect that using a timer. But you see also that when the ACK or NAC, the ACK packet is corrupted, you see in RDT 3.0 sender, what it does is do nothing. But previously in RDT 2.2, what do? We retransmit the packet, right? Of course, you can ask the sender to retransmit the packet when you see a corrupted ACK or a negative ACK, isn't it? But RDT 3.0 sender chooses to not do that. Okay, and there's a very good reason for that, and you will see in the second video ahead. Next video here is to give you an example. Okay, we will show you a few scenarios of RDT 3.0 working.
Now I'll let you ponder how you like RDT 3.0. In the meantime, let's move on and see a few examples of RDT 3.0 in action. So scenario number 1 here is the null loss scenario. So everything is going well, data, ACK. So you see, packet 0 being sent, receiver here receive 0 and send back ACK 0. ACK arriving at the sender side, yeah, receive what? Move to the wait for call from above for packet 1 state. So send packet 1, ACK 1, send packet 0, ACK 0, and go on and on and on. So this is a very straightforward scenario. Now the second scenario where we begin to see packet loss. Packet 0 go, ACK 0 comes back, packet 1 goes, but yeah, dropped. So what's going to happen here? The receiver is not going to receive anything. And the sender side has a timer, right? So that's going to tick, tick, tick until, yep, timeout. Resend packet 1 and restart timer. So ACK 1 comes in, hey, there's a timer going on here, but because ACK comes in before the timer fires, so that timer gets canceled. So packet 0 go, ACK 0 comes back. So this is the single packet loss scenario. And the third scenario is the ACK loss case. So packet 0 gets out, ACK 0 comes back, packet 1 goes, and ACK 1 get lost. What's going to happen there is the timer for packet 1 is going to tick and tick and tick until what? Expiration. So this is going to trigger packet 1 being resent, and finally ACK1 gets received, and data 0 being out again. Now, what's a bit unusual here in scenario 3 versus 2 is that, yep, packet 1 was actually received already, but it's received again because the ACK was the one being lost. Okay. No worry, because this is packet 1 and this is packet 1. For 2 consecutive packets carrying the same sequence number, receiver will not extract data and pass it further on. Receiver just send the ACK back again, okay? And that's going to clear packet 1, and therefore packet 0 can go on further.
Right, and very good question from Guanting. Yeah, so if we don't do anything receiving a corrupted ACK or a negative ACK, wouldn't that add delay? You know what? Yes, it adds delay. But check out this video. Okay, you will see that it adds delay all right, but it saves something else.
Scenario number 4 is to illustrate this case, premature timeout. So that is when the timeout interval is this long, but the ACK and data takes a long time to take a round trip back. All right. The scenario goes like this. Packet 0 goes, ACK 0 back. Packet 1 goes, ACK 1, yeah, takes longer than usual to come back. So at this time point, timer expires and packet 1 here gets retransmitted. So packet 1 gets retransmitted before ACK 1 can come back here. Right. So when packet 1 gets retransmitted, timer for packet 1 is restarted. But the good thing is, hey, ACK 1 actually just, arrived. So from the sender's point of view, what's going to happen there is sender thought, ooh, ACK for the packet I just sent has arrived, so cool. Cancel the timer and send the next packet. So packet 0 goes. And that's going to trigger ACK 0 and come back. And data 1 goes, ACK 1 comes back. Data 0 goes, ACK 0 comes back. All right. Well, I hope it's just that easy, because we are actually not yet talking about when packet 1 arrives at the receiver, what's going to happen? Well, receiving packet 1, and receiver there will see this is a duplicate because I just received packet 1, right? So this is duplicate. Ignore it. Don't pass it up to the application layer, but still generate the acknowledgement to ensure that the sender is notified. So ACK 1 will travel back. Now, sender here received ACK 1. That's right after packet 0 is sent. What does that mean? Well, the sender there receiving a corrupted ACK or an acknowledgement that's not quite in sequence number that's expected, then it's probably a negative acknowledgement. So corrupted acknowledgement, negative acknowledgement, that should trigger retransmission in version 2. But in RDT 3.0, what do we do there? We actually ignore it, right? So some of us are not very comfortable about just simply wait until the timer. But you see here, hey, this will actually not trigger any further packet being generated. Okay. You'll see an advantage in the next scenario, where if we run RDT 3.0 with quick retransmission when there's ACK corruption or negative acknowledgement. So you see here, delay ACK, timeout expires first, packet 1 goes first. And ACK 1 there generates packet 0 to go, and so on and so forth. Okay. So this generates ACK 1 to send. But if, we are not running RDT 3.0, but an RDT 3.0 with what? Retransmission upon corrupted ACK or a negative ACK, then we send what? Packet 0. Okay, again. Because obviously packet 0 is corrupted, therefore we get ACK 1. So retransmit packet 0. And that's going to trigger another ACK 0. You see, packet 1, ACK 1, ACK 1, packet 0, ACK 0, ACK 0. So for every data packet, for every ACK packet, there's going to be what? A parallel sending, duplicate of it. Is that good? Even though we try to retransmit early. Not that good either, right? Comparing this case and the previous case. So a trade-off.
So you see that it's a trade-off between delay and bandwidth consumption. All right, so Cayenne, I hope that addressed your question. Oh, Kevin now have another question. Do we have any accurate way to estimate the transmission time? Kevin, that's a very good question, and we'll talk about that next week, in fact. Yeah, because when we implement something that's similar to RDT 3.0, there's a duration, right? We wait. If it's too short, if it's too long, either way, not good. Okay, very good question. Yeah, it's a very good question. We'll learn about how TCP handles this, estimating a proper time for the timeout. But let's come back to RDT 3.0. So you guys are asking questions ahead of me. That's great. That's great. Keep that in mind. So quiz 20 is asking, let's exercise the finite state machines of RDT 3.0. And you see here that on the left is the sender. And on the right is exactly the receiver of RDT 2.2. There. So now you're asked to show the finite state machine transitions that'll be triggered in sequence. And the scenario is this. First, sender sends one packet, and the packet is received, no bit error by the receiver. And of course, the ACK comes back. The sender then sends one more packet. But in this packet, it's lost. Okay. So what will be the sequence of the transitions that would happen until the whole sender-receiver machine stabilizes? And by the way, after the packet loss, there are no more losses or bit errors afterwards. Good. So this is just to exercise, and Polly just to change the quiz problem. I have not yet worked on it, so let's compete. How about 3 minutes? Okay, go to the Slack space, grab your teammate. Let's work on this. I got it. I see that some of you got it. You just need time to type. All right, so the first one correct gets extra point. It gets a little bit challenging, isn't it? Well, guys, this is why you don't want to depend too much on last year's solutions. Yeah, because your brain gets a little bit lazy using other people's solutions. And at your age, this is probably not a good thing. But Polly understands midterms are coming ahead for many other courses that you're taking. Okay, let's see. Victor! All right, let's see. T1, T11, T4, T6. Okay, it's not exactly right. Sorry. Very close though. T12. Yeah, not quite. Yeah, just a little bit off. T13. Let's see, Cayenne. Cayenne, obviously following the lecture. Okay. Victor? You get a consolation prize, Victor. Okay, very good attempt. Okay, you also earn the extra credit. Okay, that's very brave of you. Okay, so Polly likes that. And Polly likes, of course, correct answer, of course. I don't know about you, right? I think what's more important is that you learn something instead of being correct all the time. If you think about it, life is long. It's not possible you're correct all the time. It's probably not that important that you're correct all the time, isn't it? Yeah, I think Youxiang is also good. Very good. Oh, okay. Vincent here. Okay, so this is for the first packet. Very good. The second packet, yeah, the sender sent it, but okay, typo here, obviously, right? It should be transition 8, right? Transition 8 is timeout and retransmit. And then finally, receiver N gets the packet, the second packet. An egg comes back and again, typo, okay, T9 here. The sender then finally moved back to wait for call 0 from above. Great, great. You guys all got it. Very good. Belang, you know what? You are correct as well. Zijun, very good. Yeah. Oh, is it? You can actually click it and then zoom in to look at it. Okay. Yeah, I'm not sure if you knew the trick yet, so Polly is demonstrating it. If I click into it, it would pop up and get larger. Okay. All right, so that's it. Then that's actually all for RDT 3.0. We don't have time. That's why don't we take a break and we'll talk about. So RDT 3.0 works, but there's some issue with it. Okay, and that's gonna be in the next video. But we'll come back to watch the video 10 minutes from now. It's 11:09, and we'll resume the lecture 11:19. All right, we're back online, and sorry, Vincent. Uh, hope that you don't mind that we do the calling stuff on the Google Meet session after the lecture. Okay. RDT 3.0, it works, but it's not really perfect. Let's check out why.
RDT 3.0. We spent quite a lot of time talking about it, and finally it seems to be working for the bit error case and the packet loss case. And you know what? It works indeed, okay, but it does not work that well. Okay, let me use this example here to explain. So let's suppose we have a pair of sender and receiver. In between them, there is this link, 1 gigabits per second. And the propagation delay one way is 15 milliseconds. And between the sender and receiver, the packet size is 8,000 bits. And that is the equivalent of 1 kilobyte. So this is very typical of a TCP connections packet size. And you see also earlier doing the trace routes, 15 milliseconds is very typical between two routers on a local area network. And 1 gigabits per second link, this is very commonly seen. Some of the Ethernet connections are actually 10 gigabits per second already. Now, let's try to calculate. First, the transmission time. Well, you learned already in chapter 2, right? It's the packet size divided by the transmission rate. So packet size, transmission rate, 1 gigabits per second. And we get 8 microseconds as the transmission time. Now, the performance we'll be looking at here is this, the utilization of the link between the sender and receiver. Okay. If this is high, that means, ooh, sender is actively sending all the time. So usually the throughput is going to be better. Okay. But if the utilization is low, the throughput is not going to get any better. All right. Now, in order to calculate the utilization, let's recall how RDT 3.0 works. We send from the sender one data packet, and the sender there stop and wait for data to travel to the receiver. Receiver sends back an ACK, and ACK travel the network again back to the sender. And that's when the sender can decide whether to send another data. So sender there again, stop and wait until data travel to the network, ACK travel to the network, and then send another one. So you see that the sender there is working in cycles. Stop and wait, stop and wait, stop and wait. And each cycle, it's using this much amount of time to transmit actual bits, and this amount of time, so plus the round trip wait entirely for the entire cycle. So this is 0.008 millisecond, and this part sending the packet and then wait, one wait and another wait. And here I'm ignoring the add packet transmission time because add packet is usually just very small. Okay, so that's one round trip time plus packet transmission time, 30.008 millisecond. So overall utilization on this link is very, very low, 0.00027, too many zeros. And if I illustrate the scenario I just described there, sender, receiver, and this is timeline. Okay, at time 0, first packet bit is transmitted. So right here, first bit goes onto the link, and it takes this amount of time. That is the time to transmit all bits on the packet. So last packet bit transmitted is right at this time. Okay, that is the packet transmission time, L divided by R. And these bits is going to travel halfway to the receiver and another halfway back to the sender. So first packet bit arrives right here. This is what? The propagation delay. Okay? And this is also propagation delay. So 2 propagation delay plus L divided by R. This is one cycle. Within a cycle, only this amount of time sender is being active. Okay, only this amount of data is being transmitted while the entire duration, right? The sender can just keep pushing bits out, okay, onto the network interface. So you see again, the network utilization, L divided by R over the entire term, RTT plus L divided by R. Very low utilization. And that low utilization can be translated here. The throughput on the 1 gigabit link is only 270 kilobits per second. this is not even enough to send any video that would be sensible. So you see here, RDT 3.0, the design itself, although it works, but it limits the use of the physical resources. Okay, we're only sending one packet and then stop and wait until we can send another one. Now that I show this plot, then you know, yeah, obviously to increase the utilization is to send multiple packets per round. Indeed. So let's look at the plot in a bit more detail, just like we did in the previous slide. So sender, receiver, and timeline again. So this is the time we send the first packet, the end of the first packet. This is the time, first bit arriving at the receiver, last bit arriving at the receiver. At this point, the receiver can send back acknowledgement. So this is the time the acknowledgement arrives at the sender. This is the sender can begin sending the next round of packets. So how long is a round this time? Well, this is one-way delay, right? This is also one-way delay. So round trip delay plus L divided by R. So the same. In each cycle, we now send multiple copies of packets. So now we're sending 3, so 3L divided by R, right? So utilization is now 3 times higher than the stop and wait scenario.
Yeah, so cool. So let's learn about pipeline RDT. So in this video, I'm going to give you the general idea and a big overview of the 2 kinds of pipeline RDT that we'll talk about next.
And this takes us to this new class of RDTs called the pipeline protocols. Okay. What it said is, let me repeat myself, the sender allows multiple packets being sent per round, okay, or multiple packets in flight. By in-flight, I mean that these are just data packets going out. They are not yet acknowledged. So it's illustrated better here. So this one on the left is stop and wait. This one on the right is the pipeline RDT. So we see multiple data packets go, not yet acknowledged, and their acknowledgements will come back in a sequence, okay, in a round to the sender. Okay, so a range of sequence number needs to be increased. So previously in RDT 3.0, we used just 1 bit, right, 0, 1. But now we need to allow multiple packets going out simultaneously. And we need to make sure that we acknowledge each of these packets. So we need to tell each of these packets in flight apart. Well, the sequence number definitely needs to be expanded. And we'll need buffering at the sender and the receiver side as well. Because, hey, what if multiple of these packets in flight are dropped? They need to be retransmitted again. So buffer definitely at the sender side is required to store those packets that are not yet acknowledged. Receiver here will also need buffer space because when this packet is lost and there's other packet coming in subsequently, should we keep them or should we drop them and have the sender retransmit again? And what about these other packets that has already arrived? Okay. So there's some buffer space also, okay, needed in order to address different needs of different designs. So buffering required, a longer range of sequence numbers required. Okay. Now, in the next few slides, what we're going to introduce are just 2 different flavors of these pipeline protocols. So they are the big categories. First is the go back end. The second is selective repeat. Now, one can, of course, further tune the go back end so that it works slightly differently. Hopefully, the second version works slightly better than the fundamental version. Similarly for the selective repeat protocols. Okay, so here's the overview slide that contrasts the 2 big categories of pipeline protocols. On the left, the go back end. On the right, selective repeat. Right? They are the same this way. Both of them allow having multiple packets in flight in a round. Okay? Well, that's the basic ideas of pipeline protocols. They must be the same this way. And then everything else will be different. First of all, okay, what the sequence number in the ACK packet means, very different. One is to indicate I'm acknowledging an individual packet. So when the receiver in selective repeat sends an acknowledgement, that sequence number in the acknowledgement is to acknowledge exactly the data packet carrying that sequence number. But for go back end, the receiver sends back acknowledgements, but the acknowledgement carries a sequence number such that all the data packets before that sequence numbers are acknowledged. So this is a bit odd. Okay, so that one sequence number seems to be acknowledged all the packets before that. But the fact is that what the receiver is doing is this. The receiver will not add packets if it arrives and the receiver finds that there's a gap in between. So packet 1, 2, 3 missing, 4. Okay. When 4 arrives, the receiver does not send back acknowledgement 4. Instead, it sends acknowledgement 2 because there's a gap in the middle. So what the receiver of go back n here is saying is, I'm actually telling you to which point I do have consecutive receive data packets. So the next one is, the beginning of a gap, definitely. And the two categories work also very differently here. Timer. Okay, if you recall in RDT 3.0, we need a timer in order to tell whether a packet is dropped or not. Yes, go back in and selective repeat. Both of them implements timer. Okay, but in selective repeat, there's one timer for each packet that is still in flight, not yet acknowledged. Okay, so one timer, one packet. But for go back in, there's only one timer for the oldest unacked packet. So in one round, there'll be a lot of packets being sent, multiple packets being transmitted. Okay, there's going to be just one timer for the oldest unacked, meaning if you send one flight out, there's just going to be one timer for the first one in that flight. Okay, and if the first one is acknowledged, there'll be a timer for the second packet, that is now the new oldest packet that's not yet active. Okay, so one timer for a flight of packet in go back in. And the last difference is this. Okay, for selective repeat, when timer expires, the sender only retransmit the unacked packet. So whatever that timer says, if this is for sequence number 10, then it only retransmits packet 10. But in go back in, when the timer expires, it's going to retransmit from that oldest unacked packet. So all the unacked packets from the oldest one to the newest one. All right, so each timer is going to trigger retransmission of the rest of the flight of the packets.
Okay, so that's the overview. Between go back in and selective repeat, which one do you like better? Okay. Selective repeat is more intuitive, right? One act, one data packet. One timer per unacked data packet. Okay. And go back in, it's a little bit weird, right? So you have one act for a train of data packet. And you have one timer also for a train of data packet, but that timer is associated with the first, in the train, first packet in the train. So the way they work quite differently. Okay. So in the next hour, as well as next week, beginning of the next week, we'll go over the details of go back in and selective repeat. Now let's start with the go back in, GBN, the basic idea.
Now let's look closer into the first categories of the pipeline RDT, the go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number in go back in. If you recall in RDT 3.0, we only allow one data packet goes in out without being acknowledged, isn't it? And in that case, we just need one bit sequence number to tell the old packet and the new packets apart. But now go back in being a pipeline RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k subtracting 1. And next, in go back in, or generally the pipeline RDT, we do have this thing called a sending window. And the sending window is usually associated with a limit, we call the n, or the sending window size. Okay, so N here is to limit the number of unact packets allowed. Right? And go back in, this is the number of consecutive unact packets allowed. It's also illustrated here. Okay. From the first packet in flight to the last packet in flight, the max range is N. Right? So at any given point in time, we allow only up to N packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And N here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit N, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than N. All right. Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window N. All right? And the last one, so these blank ones are simply outside of the window limit, so not usable. Right? And here, let's assume, okay, send base here, finally receive an acknowledgement, and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first unact packet, so we actually need to what? Change it to this packet sequence number. Right? As a result, we shift the window, and it's beginning from here, and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. Okay, so such a window is also called the sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go back and sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet, and as a result, it needs to be moved to the sequence number of the first yellow packet now. Right? And you see window then here is sliding over by one. The next seek num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is useful and not yet sent. So because when we get a call from above and if we need to generate a data packet, then we'll turn this blue one into yellow. And the next seek num is going to be shifted over and reassigned to the first blue packet after sending. And we do not shift the window size at all because the send base is not changed and the N here is a constant. But be careful though. There will be scenarios where, hey, all these blue ones are actually yellow, meaning, the sender does have large message to send and we are actually exhausting the entire window size to send the message already. in that case, the next seek num will be pointing here at a blank packet. Okay, that is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, yeah, there's no blue packet at all. All right, so next seek num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet. The rest of the Go backend you heard a little bit already about. The AG, the sender received, is going to be a cumulative AG. Okay? What it means is that in the sequence number of the cumulative AG, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. All right? Now, if the sender receives duplicate acknowledgements, so hey, AG n has already been received, but the next moment, another AG n is received. What does that say? If you recall earlier, yeah, that usually meant, oh, packet n+1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate AG at sender side indicates, yeah, whatever n is plus 1 is a packet that's missing. Timer. Yeah, there is only one timer for an entire flight of an AG packet. So it's a timer associated with the base, okay, of the in-flight an AG packet train. Okay, so that is essentially this. Yeah, the oldest in-flight an AG packet is always indicated by the send base. In a way, yeah, there's a timer associated with the send base essentially. Whenever the send base is changed or whenever the send base is refreshed, we refresh the timer or restart the timer. If it's a bit unfortunate, then we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet, starting from n all the way to the highest number that's not yet AG. So that means starting from the send base all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.
And that takes us to quiz 21 and the last week this week. Okay, so let's try to exercise what we've heard there in the video. And guys, congratulations. That video was almost 9 minutes long. Okay, one of the longest video you've seen. Okay, so if you survive that, you are getting accustomed to online teaching. Yeah, and you see that we need 10D. More sequence numbers to track which one is lost, which one is new, which one needs to be retransmitted. And now, quiz 21. Okay, so again, you see a window of n. And the send base is currently 23, isn't it? The next seek num, the next sequence number allowing packet to be sent, number 33. And the blank packets in the video, I now use gray as a different color, but the gray packets are essentially the blank packets there. So the first gray packet is another variable that's currently 39. Okay. Okay, so send base is the first packet of a train of packet in fly. Okay. Next seek num is the sequence number if the sender needs to generate the next packet. First gray packet is the first blank packet, okay? The first packet outside of the window, okay? Q1, Q2, Q3, they are independent, all right? So Q1 asks, given 23, 33, 39 for these three variables being the current value, what would the three variables values are after sending 3 more packets? Okay, Q2, given 23, 33, 39. If we suddenly receive an AG with n being 24, what will be the values, okay, after receiving this AG? Q3, similarly, starting from 23, 33, 39. If we suddenly receive an AG for 32, how would these three values be changed? Okay, good. Now go to the Slack space and work on quiz 21. And you have 3 minutes for this. Okay. Should be quite straightforward if you are following the video. Okay, hey guys, did I say independent? Yeah. Sorry, Zijun Naiming, you might want to update solutions. So Q1, Q2, Q3 are independent. So they all start from 23, 33, 39. Okay. So you guys are too quick. Team 1, Team 8. Okay. Very smart, guys. There, finally, Jade is paying attention. Good. But I see that you guys got it. Zijun and Naiming. This is great. Not bad at all. But sometimes you want to give it some time. So read the whole question before you start working on it. In fact, when we were grading the exam 1, we saw students did not read through the whole question and started working on it, assuming that it looks very similar to one of the old questions. Okay, great, Naiming. You're very quiet during the class, but I see that you're following. Very good. There we go. Good. I think you guys pick up the idea. I think the hardest part, I think go back in is actually harder for human to simulate. Selective repeat is actually more straightforward. And the exact reason that go back in is a little bit hard for human to simulate is because there are multiple packets that you need to handle at the time. And it's a train of packets, not like individual ones. Yeah, so the first thing you need to do is to make sure that you know what symbase means, what next seek num means, and what the first grade packet means. Okay, they kind of all indicate very important sequence number in a window. All right, great, perfect. So we can now come back to get into the details of go backend's finite state machine. Let's start with the sender side. Okay, first video is short. Let's just get it started.
Go backend sender's finite state machine. Before we start talking about this, let me review RDT 3.0 sender's finite state machine. And here it is, the RDT 3.0 sender. Okay, so we're starting here. Okay, and there are 4 typical transitions: 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted and it is indeed the act we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these 2 conditions on purpose. The second condition is, yeah, we get an ACK all right, but this is what carrying 1, which indicates this is a negative acknowledgement. Right? So in these 2 cases, instead of quickly retransmit, we just ignore. Right? So this is a quick refresh of RDT 3.0.
Now the real go back and sender side finite state machine. So this one is a little bit long, about 5.5 minutes.
In go back and sender finite state machine, we also have these 4 transitions: getting a call from above, receiving feedback from the receiver and it's not corrupted, having the timeout event, as well as getting feedback from the receiver but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seek num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seek num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give it the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because go backend is a pipelined RDT, meaning there will be multiple packets in flight, so they'll be generated, being transmitted, but not yet acknowledged. So these send packets will need to be stored temporarily at the sender before they are acknowledged, because chances high that you need to retransmit it somewhere later. Okay, so we need an array instead of just one packet there to store the packets that are in flight. Next step, send the packet out. Oh, and then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2. something is to have these timers. So we need to start timer, definitely. But in go backend, we have one timer for the entire flight of NAC packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in go backend is associated with the first yellow packet, so associated with the base. So only when the packet we are generating is the base, then start timer. Otherwise, don't. So this ensures that we have only one timer for one flight of NAC packets. And the last is straightforward, just increment the sequence number by 1. Right? So this is if the next seek num is within the window. Otherwise, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. All right, so this is supposed to be the case where we receive acknowledgement, and it's a new one, therefore we could move on. All right, so let's take a closer look at how the move on is like in go back and sender. First of all, the checking condition. Get a feedback packet coming from the receiver from the lower layer. And if it's not corrupted, oh, good. So the feedback packet is not corrupted. So this must be one of those cumulative acts. So inside the act, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get act num. Okay, so this is a new function call introduced into go backend's finite state machine. So that is just a bit abstract, but what it does is to get the sequence number in the cumulative act packet here. All right. And we simply change the base to that sequence number plus 1. All right. So this is the first packet that is an act. Hey, makes sense, right? Receiver sends a cumulative act. So that act carries the sequence number n, which indicates all the sequence numbers before that, including n, are acknowledged. And the n plus 1 is the first in the gap in the receiver. The first one, that act cannot be acting. Okay, therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is nulled, the next seek num. What does that mean? Base should be the first yellow. And next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet act at this point in time are already act. Okay, so stop timer because there's no pending packet, okay, waiting for acknowledgement. Otherwise, yeah, restart timer. So we receive a cumulative act. The base is reassigned such that it's pointing to the first yellow packet. Okay? And so we refresh the timer for the first yellow packet for the base. Okay? So restart timer. Right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones certainly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore, we need to restart the timer, okay, for the refreshed first yellow packet.
All right. So you see that these are the most important transitions in go back and sender. It gets a little bit complicated. And by the way, in the pseudocode, you see there that base is what Polly meant by send base earlier in quiz 21. Okay. And Hongru was asking about quiz 21. The next seek num should be 25 since we don't get egg for 25. The base should be send base should be 25 because we have not yet get the egg for 25 yet. Next seek num is to indicate in case the sender wants to send the next packet. Okay, what is the next available sequence number to you? So the next seek num is always blue or gray. Okay. Now when next seek num is taken and sender is sending a data, then that blue number there will turn yellow. Okay. I hope I addressed the question, Vincent. Let me know. Keep asking until we get it right. Okay, good. There's just one more short video for the sender side of sender side of go back and FSM because there are two more transitions. Remember.
And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. Yeah, we restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only one packet, but this time in go back in, we retransmit for the entire flight of packets starting from the base to the packet right before next seek num. And the fourth transition is this: when the sender received a feedback and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In go back and sender, yeah, it's actually handled here. When the sender receives an ACK, it's not corrupted. Whether it's a new ACK or a duplicate ACK, the actions are the same. If it's a new ACK, the base will shift to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Yeah, some of you might not be very comfortable with this, right? Because hey, if the base remains the same, what do we do here? Yeah, we'll be definitely in this situation, right? Yeah, there's an unact packet somewhere and the base remains the same. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval for that base. How do you like that? Think about it. And the last bit of the go backend sender, or shall I say the first bit of the go backend sender that we actually talked last, is the initialization of the sender. Okay, so the base, starting of the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In go backend sender, textbook authors decide suddenly that they want to start from the sequence number 1.
All right. So we are yet to find out how the receiver side of go backend is working. But Vincent, by the way, you are asking a very good question. I see that you are a little bit confused. But you know what? Many of the guys attending the lecture might also have the same confusion. I know why. Because I said, right, Polly said, go backend uses cumulative acts. You use one act to acknowledge all the packets before that sequence number. And so then it's easy for you to associate such that, oh, in go backend, you send a train of packet and you get just one act to acknowledge all the packets. I think that is probably what you're thinking. But you know what? It's not quite like that. If you recall that go backend RDT picture, we send multiple data and the acts, there are also multiple of them coming back. So cumulative act there meant only that the sequence number indicates it's the last packet received okay. So if you receive a high number and the sender thought that, hey, there are actually quite a few yellow packets, but hey, whatever that number says, all the packet before that, all those yellow packets will turn green. Okay? But that doesn't mean you only get one act for the train of packets. You still get many acts for a train of packet, in fact, in go backend. All right. So if you recall the sender side, once we receive an act, right, we actually shift the send base by 1 and we restart the timer. Yeah, so we wait for the timer for that packet. Or that packet starting a train. You see. So there'll be another acknowledgement back for that packet or for a few packets after that. So even though we receive one act for 25, for 24 or for 25, 24, we only acknowledge packet 22 and 23. 23 and 24. Okay, the next packet that's yellow is 25. And so we will still need to wait until these yellow packets are being acknowledged. Okay, they will never turn blue, in a way. Okay. All right, great. And that is a very common confusion, in fact. Okay, Vincent, I'm very glad that you asked that because many other classmates might have the same confusion. Now, the receiver end of GBN.
Now, the receiver finite state machine of go backend. It's actually quite simple. Let's just skip the initialization and focus on the two transitions possible. Among the two, this one is the more straightforward. We receive a data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for go backend again. So what it does is simply, checking the sequence number in the data and see if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate act packet for packet sequence number 1, send the act out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the ACK packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, so there's no extract of data, no passing of the data up to the application layer, and all we do is simply react to the data with the highest sequence number arriving correctly in order. So go back and receiver there. Works a bit odd, not that intuitive, but it's very simple. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number, and that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.
All right, so that's the receiver end of go back in. The semantics of the ACK is still indicating the packet last received okay. But unlike RDT 3.02. something, it's stop and wait. So it's last packet receive okay. In go back in, you might have several packets, and so the sequence number there, receiver is sending, indicates the last packets received okay, and that last packets will need to be consecutive. All right, so no gaps. So that sequence number says, if it's n, all these packets before n, including n, they are received okay. All right. So if there's a gap that the receiver discover packets being received, it sends still the earlier number where the packets receives that are in order. No gaps. Good. And that's all the time we have this week. We have like 3.5 minutes remaining, but the next topic is examples. And go back and as you see that, it's a little bit hard to simulate, right? And you start getting confusions like Vincent did. So this example, it would take us some 12 minutes of time to just get through it, one example, But it's actually very important that we go through it in detail so that your confusion is cleared. So we'll call it a day and we'll call it a week now. If you have further questions, feel free to type them up. And if you have not yet completed the quizzes today or yesterday, please do. Complete all the WA quizzes. With that said, happy weekend. Enjoy the rest of the day. Bye. And of course, those who would prefer talking to me on Google Meet, feel free to tune in. But I'll stay on for some few more minutes until it's the end of the lecture time. And then I will end the stream. And then you can talk freely without being recorded by YouTube. Good. So, bye. Oops. One more time. Oh, by the way, if you have not yet left the classroom, just one more thing. What's important is to learn. Grades, take things easy. This is just to prepare you guys mentally for the exams to come. And for the grades that we will be releasing later in the afternoon. And by the way, recall the Lord of the Ring quiz. So you have a problem at right now that is challenging, right? And you're puzzled. But you see, Polly said that, hey, you can try to relay this problem and find other problems in other domains that are similar, right? Like Polly read the books, the Lord of the Rings. I thought, hey, that was the same problem. It's a very interesting solution they have there in the book. I borrow that. We can borrow that. But you see, if Polly did not read the Lord of the Rings series, right, Polly would not have the association. So the point of college education or education in general is so that you know enough things so you could have something, okay, have a base that you can associate when you run into trouble or run into problems that you need to solve. Or given problems you need to solve in exchange of money so that you can buy food. All right, so yeah, study, read, work hard, but it's not necessary to stretch yourself out, to over expect of yourself. Whatever grades you receive, take it. It's always fair. All right, and I know some of you very, very smart. Try to be humble. It's gonna be good for you. Okay, good. All right, too much talking today. You know what? It's time to end the session as well. So those who want to speak with Polly, feel free to call in.